In this lecture, we are going to study a specific property of the op-amp called slew rate. Before we study that, we actually need to understand a particular characteristic of the op-amp, namely the what are called the large signal transfer characteristics. So what I am interested in is calculating ID1 minus ID2. So in other words, this is the differential current flowing through M1 and M2. I want to find this as a function of the differential input voltage which is applied, and so which is V in 1 minus V in 2, that is delta V in. So in other words, I want to plot ID1 minus ID2 as a function of V in 1 minus V in 2. Now to do that, I need to first calculate analytically ID1 and ID2 or the difference as a function of the input voltages. So to do that, I need to write down the current equations of the op-amp, of the transistors. So first of all, let us assume that the total current through the op-amp is 2I0, so that each of M1 and M2 has a current I0. So before we write it in this manner, so we can write the voltage at node XY as V in 1 minus VGS1 or V in 2 minus VGS2. So clearly these two quantities have to be equal. This means that V in 1 minus V in 2 has to be equal to VGS1 minus VGS2. Now what do we know about VGS1? VGS1 is nothing but Vt of the transistor plus root of 2ID1 over mu n C ox W over L. And similarly, VGS2 is Vt plus root of 2ID2 over mu n C ox W over L. So therefore, V in 1 minus V in 2 is equal to root of 2ID1 over mu n C ox W over L minus root of 2ID2 over mu n C ox W over L. This is the first relation. I'll denote this as equation 1. This is the first relation between ID1, ID2 and V in 1, V in 2. Remember that V in 1 and V in 2 are the known variables and ID1 and ID2 are the unknown variables for this particular calculation. The second relationship is simply KCL at node XY, which tells us that ID1 plus ID2 always has to be equal to 2I0. So I'll denote this by equation 2. Clearly, I have two equations and two unknowns, so I should be able to solve for ID1 and ID2. But more specifically, I am interested in solving for ID1 minus ID2. It turns out that if you solve these equations for ID1 minus ID2, you'll get the following relationship. So you can of course do some arithmetic manipulation. So it turns out that ID1 minus ID2 depends on V in 1 minus V in 2 in the following manner. So ID1 minus ID2 is half mu n C ox W over L into V in 1 minus V in 2 times square root of 8I0 over mu n C ox W over L minus V in 1 minus V into the whole square. So clearly ID1 minus ID2 is an odd function of V in 1 minus V in 2. Now what happens when V in 1 minus V in 2 is 0? If that happens, clearly ID1 should be equal to ID2, which means they are both equal to I0. So this equation is clear on that. Now if V in 1 minus V in 2 becomes large enough, it turns out that this equation is no longer valid, because we have assumed in writing down these equations, we have assumed that both transistors are in saturation. If V in 1 minus V in 2 is large, one of the current starts decreasing, the other current starts increasing, because clearly ID1 minus ID2 is finite. So one goes out of saturation. So this is something to keep in mind. So if you were to plot ID1 minus ID2, as a function of V in 1 minus V in 2, it turns out that for very small V in 1 minus V in 2, this particular relationship is linear, because you can assume that you can linearize this particular expression to get a linear dependence. If V in 1 minus V in 2 becomes large, it turns out that this particular relationship becomes non-linear in some manner that you can determine by plotting this curve. Now what we are interested in are a couple of points on this curve. So first of all, we are interested in finding out what value these 2 points are. So clearly when this happens, you can see that ID1 minus ID2 becomes a fixed value, and that happens when one of the transistor goes out of saturation into cutoff. When that happens, let us say M2 turns off, then all of the current flows through M1. In other words, this total current has to be equal to 2I0. On the other side, if V in 1 minus V 2 goes negative and large, all of the current flows through M2, and therefore ID1 minus ID2 is minus 2I0, because ID1 becomes 0 and ID2 becomes minus 2I0. Now another property of this is that the slope around the origin has to be equal to the derivative of ID1 minus ID2 over dou V in 1 minus V in 2, and from small signal analysis we know that this is equal to GM of the differential pair, and that is why it happens to be linear around the origin. Now of course, once it reaches this point, the transistor no longer has any transconductance. For example, if you were to plot the transconductance of the device, the transconductance of the differential pair as a function of delta V in, it would look something like this. It would go to 0 at some point. Our job is to find out at what point this full switching happens. In other words, I am trying to find out at what voltage, the current fully switches from one side to the or fully switches to one side. It turns out that happens when the gate source voltage of one transistor falls just exactly to its threshold voltage, and that can easily be calculated now as delta V in. I'll call that delta V in 1. This delta V in 1 happens to be equal to root of 4 I naught over mu 1 Cox W over L. Now I'm going to rewrite this in a specific manner. I'm going to rewrite this as root 2 into root of 2 I naught over mu n Cox W over L, and you can clearly see that this is nothing but root 2 times VGS1 minus VT at the quiescent point. So if you were to take the quiescent point of the differential pair and calculate the VGS1 minus VT, which is the overdrive voltage or the VD sat of the device, and if you were to apply root 2 times that voltage at the input of the differential pair, all of the current would switch to one side, and that is this point delta V in 1. Now we are interested in this for a very specific reason. We are now going to study what will happen if you start applying incremental steps to the input of the op-amp. So I am going to take the op-amp and I am going to start applying incremental voltage steps. So delta Vd by 2 and minus delta Vd by 2. So in other words, I am applying an incremental voltage, differential voltage of delta Vd at its input. And let us say that the op-amp is driving some load capacitance CL. As we have seen before, the op-amp normally drives a capacitive load because transistors present a capacitive load when seen from the gate. Let us say this output voltage is V0. Now, if I were to apply a differential voltage delta Vd, let us first start by assuming delta Vd is small. If delta Vd were small, I can calculate what I0 is. I am now going to write down the total currents through the transistor. This current is I0 plus some I0 plus some delta I1. This current is I0 minus delta I1, where delta I1 is equal to GM1 times delta Vd by 2. Of course, what is going to happen is that this current is going to flow through M3 and get mirrored down to M4. So current through M4 is I0 plus delta I1, and so the incremental current, total incremental current of 2 delta I1 flows through the capacitance CL. So I0 is 2 delta I1, which is clearly GM1 times delta Vd. So clearly the one stage op-amp acts like a transconductance of value Gm. If I were to replace it with a block diagram, it would look like this. It would look like a transconductor whose value is small Gm1. So this is delta Vd by 2 minus delta Vd by 2. This is what the model of the op-amp would look like. So if I were to plot the input and output voltages, so let me first plot the input voltage. So I'm giving a small step voltage in the input. The output voltage now, remember the x-axis is time, and here this is delta VD and this is VO. So for this particular delta VD, let me call that delta VD1. So IO is equal to GM times delta VD1. So this is IO1. And for the capacitance, I can say CL dVO by dt is equal to IO1, because all of this current flows through the capacitor, and therefore dVO by dt is IO1 by CL, which is GM delta VD1 by CL. Clearly, the dVO by dt is a constant because delta VD1 is constant, CL is constant, and GM is constant. Therefore, the output rises as a ramp because the output current is constant. Now let us say I increase the value of delta VD1 to delta VD2. I apply a larger step at the input. In that case, dVO by dt is equal to GM delta VD2 by CL, and so on. So it would rise with as a faster ramp. Now, if I were to apply a large enough step, if I were to apply larger and larger steps, let's assume I apply a very large step delta VD3, what would happen is that the largest current that can flow out of the device is clearly limited, because at that point what would happen is all of the current 2I0 would flow through M1. So this current is 2I0, this current is 0, and this 2I0 current flows through M3 and flows out of M4 into the output. Now please note that in this case dV0 by dt no longer depends on delta VD, it is simply 2I0 over CL. So this ramp would rise at the rate of 2I0 over CL. Now the important thing to note is that if you were to increase the slope if you were to increase delta VD any further, you would not get any further increase in the slope of the output voltage. That is important to remember. So I'll just write down the slope numbers here. This slope is GM delta VD1 by CL, and this is GM delta VD2 by CL. So it is important to remember, if delta VD is larger than delta VD3, VO slope remains as 2I0 over CL. You cannot charge the capacitance any faster. In such a case, so the OpAmp is said to slew, and the maximum rate at which the OpAmp can charge or discharge a load capacitance is called the slew rate. So the slew rate is the maximum rate of charge or discharge of the load capacitance. So let us now find out what the slew rate of the op-amp is. So let us take this op-amp and let us apply a positive step, and let us assume that the op-amp is charging some load capacitance CL. As we have seen, in this particular condition, the M1, assuming that this is a positive step, M1 carries all of the two current current 2 I naught, M2 has 0 current, this current is 2 I naught, M4 carries 2 I naught, and that is the rate at which the capacitance is charged. So the positive slew rate is said to be 2 I naught over CL. Now what happens if a negative step is applied? Let us say you were to apply minus delta VD by 2 to M1 and plus delta VD by 2 to M2. If that were the case, M2 would have a current 2 I naught and M1 would have 0 current, M3 would have 0 current, M4 would have 0 current. So M1, M3 and M4 would be cut off, and all of this current would be pulled out of the capacitor CL, so that CL would discharge at a maximum rate of 2 I naught over CL, and this also happens to be the negative slew rate.